Good morning, students. In the earlier video, we had discussed about how to determine the acidity of a solution. In this video, we will be discussing about the basicity of the solution. But we will just recall the content which we had done in the earlier video so that it will be a revision for you all. In aqueous solution of any substance, if the concentration of hydronium ion is more than 10 raised to minus 7 molar, the aqueous solution becomes acidic. Or if the concentration of hydroxide ion is more than 10 raised to minus 7 molar, the aqueous solution becomes basic. Now for acidic solutions, the hydronium ion concentration is greater than 10 raised to minus 7 molar. So the value of pH is always less than 7. The acidity of a solution increases as the concentration of hydronium ion increases in aqueous acidic solution. So pH decreases. I repeat, acidity of a solution increases as the concentration of hydronium ion increases in an aqueous acidic solution. So pH decreases. Now, if the concentration of hydronium ion decreases, the acidity of a solution decreases. So pH increases. It is totally the opposite of the first case, in which acidity of a solution increases as the concentration of hydronium ion increases in an acidic solution. So pH decreases. Whereas in the second instant, the concentration of hydronium ion decreases, so acidity of the solution decreases, but pH increases. The aqueous solution having pH 2 is more acidic than the solution having pH 4. Example, hydronium ion concentration is equal to 10 raised to minus 2 molar. Is, as we had seen in mathematical representation, pH is equal to negative logarithm to the base 10 of hydronium ion concentration. That is negative log to the base 10 of 10 raised to minus 2 molar. As we are studying logarithm, the power comes as a coefficient of that particular content. So minus into minus plus 2 log 10 to the base 10. Log 10 to the base 10 is 1. So 2 ones are 2. The second one is the hydronium ion concentration is 10 raised to minus 4 molar. So as per the mathematical representation, pH is equal to negative logarithm to the base 10 of hydronium ion concentration. That is negative log to the base 10 of 10 raised to minus 4 molar. So minus 4 comes forward, minus into minus plus 4 into log 10 to the base 10. So that is 4 log 10 to the base 10. Log 10 to the base 10 is 1. So 4 ones are 4. We'll just see how does the pH varies in an aqueous solution. pH of aqueous solution, if the values, if we write it down from 6 to 0, when pH decreases, the acidity increases. So if pH is 6, the acidity is less. But if the pH is decreasing, that is 5, 4, 3, 2, 1, you can see there is an increase in acidity. Moving on further to the content related to basic solutions. Now pH, the concentration of hydroxide ion is written mathematically as negative logarithm to the base 10 of concentration of hydroxide ion in aqueous solution, which is known as POH. pH, that is the concentration of hydroxide ion, is written mathematically as the negative logarithm to the base 10 of the concentration of hydronium ion in an aqueous solution, which is known as POH. POH is mathematically represented as negative logarithm to the base 10 of hydroxide ion. I repeat, negative logarithm to the base 10 of hydroxide ion. For basic aqueous solution, if hydroxide ion concentration is greater than 10 raised to minus 7 molar, then POH will be less than 7 and pH will be more than 7. I repeat, for basic aqueous solution, if the concentration of hydroxide ion is greater than 10 raised to minus 7 molar, POH is less than 7 and pH is greater than 7. In aqueous basic solution, as the concentration of hydroxide ion increases, the basicity of the solution also increases and pOH decreases. But when pH increases, if the concentration of hydroxide ion decreases, the basicity of the solution also decreases. pOH increases, but pH decreases. One more time, in an aqueous basic solution, as the concentration of hydroxide ion increases, the basicity of the solution also increases and pOH decreases, but you are able to see an increase in pH. But if the concentration of hydroxide ion decreases, the basicity of the solution also decreases, but pOH increases and pH decreases. Due to the increase in pOH, we are able to see the decrease in pH. As we have seen in acidic solution, aqueous solution having pH 12 is more basic than the aqueous solution having pH 9. For neutral aqueous solution, the hydronium ion concentration is equal to hydroxide ion concentration. That is equal to 10 raised to minus 7 molar. So the pH will be 7. I repeat, for neutral aqueous solution, the hydronium ion concentration is equal to hydroxide ion concentration. That is equal to 10 raised to minus 7 molar, which is representing pH as 7, which is for neutral solution. The most important question for 2 marks, derive pH plus pOH equal to 14. Now as seen earlier that distilled water is neutral here at 298 Kelvin temperature, that is 25 degrees Celsius. The hydronium ion concentration and hydroxide ion concentration is equal to 1 into 10 raised to minus 7 molar. So multiplying both the concentration, hydronium ion concentration into hydroxide ion concentration, it is 10 raised to minus 7 into 10 raised to minus 7. That is, according to the law of multiplication, it turns out to be 10 raised to minus 14 molar. Now applying logarithm on both the side, that is to the LHS and RHS, LHS logarithm 10 to the base of hydronium ion concentration plus logarithm to the base 10 of hydroxide ion concentration is equal to logarithm to the base 10 of 10 raised to minus 14 molar. Now logarithm of 10 to the base hydronium ion concentration plus logarithm to the base of 10 of hydroxide ion is equal to negative 14 log 10 to the base 10. Now multiplying negative on both the side, negative logarithm to the base 10 of hydroxide ion solution minus negative log to the base 10 of hydronium ion concentration is equal to 14 log 10 to the base of 10. Now as we had seen earlier, negative log 10 to the base of hydronium ion concentration is pH, negative log to the base 10 of hydroxide ion concentration is pOH. So pH plus pOH is equal to 14. We'll just take this content one more time. That is, in distilled water at 298 Kelvin temperature, that is 25 degrees Celsius temperature, hydronium ion concentration and hydroxide ion concentration are equal, which we had seen earlier, that is 1 into 10 raised to minus 7 molar. The hydronium ion concentration and molar hydroxide ion concentration, when multiplied, the molarity also gets multiplied. By the rule of multiplication, the power gets added. It is 10 raised to minus 14 molar. Applying logarithm on both the side, log to the base 10 of hydronium ion concentration plus log to the base 10 of hydroxide ion concentration is equal to log to the base 10 of 10 raised to minus 14 molar. That is log 10 to the base of hydronium ion concentration plus log 10 to the base of hydroxide ion concentration, that is equal to negative 14 log 10 to the base 10. Multiplying on negative on both the side, negative logarithm to the base 10 of hydronium ion concentration, negative log 10 as a base to hydroxide ion concentration is equal to 14 log 10 to the base 10. As you can see, negative logarithm to the base 10 of hydronium ion concentration is pH, and negative logarithm to the base 10 of hydroxide ion is pOH. So pH plus pOH is equal to 14. As we had seen earlier for acidic solution, the pH of aqueous solution for basic content. As you can see, the basic values start from 8. So as you move from 8 to 14, the pH increases. That is, the basicity of the solution also increases. When the pH value of the aqueous solution increases, then the basicity of the solution also increases.